Well, it's good to be back here at the annual Intelligent UK RF and Microwave Design Seminar. I think this is now firmly established on the Cambridge calendar. As Helen mentioned, I'm going to be talking about power amplifier MMICs for mmWave 5G. In Costas's talk earlier, he highlighted just how crucial these are in the performance of 5G equipment. So I'm going to start by looking at the likely operating bands. I'll then look at the solid state processes, have a review of those processes and what they can offer us. We'll then move on to look at packaging technologies, specifically SMT packaging technologies for high volume manufacture. I'm then going to discuss a number of practical mmWave 5G PA design examples. There's a 28 GHz PA, which was in an overmolded SMT plastic package. Then there's a 39 GHz PA that was also in a plastic SMT package, but an air cavity. Then a dual channel 26 GHz PA. And this was in a custom laminate package. Then a dual band PA, which looked at the 26 GHz and 32 GHz bands, all on the same IC, electronically switchable between the bands. So, what operating bands will win the day for mmWave 5G? In Europe, about a year ago, the Radio Spectrum Policy Group identified the 26 GHz band from 24.25 to 27.5 as what they call the pioneer band for 5G in Europe. And they're encouraging all EU members to keep part of this spectrum available for 5G. In the US, the FCC rather stole a march on them by some time before, announcing license bands at 28 GHz, 37 GHz and 39 GHz bands. More recently, they've also announced 24 GHz. There's going to be an auction in the US very soon this month for the 28 GHz bands. Auction 101 if anyone fancies bidding. And straight after that, they'll auction off the 24 GHz band. And this is split into two big chunks, and that's auction 102. There's some additional European bands that the Radio Spectrum Policy Group mentioned. And that's a 32 GHz band, which they call a future band, and a 42 GHz band. So what are our process options? Well, you can make PAs at mmWave frequencies in CMOS. The gate lengths are short enough for the transistors to operate quite nicely. SiGe, gas p-hemp, and GaN. Now, as these are listed here, the cost per unit area goes up. The power density also goes up, however. Now, these values here, these are what I believe is the sensible saturated RF output power level for a commercial part in each of these technologies. Now, I'm not saying you can't find a paper somewhere where somebody has demonstrated a higher output power in one of these technologies. But if you're looking for commercial products today, these are the power levels you're looking at. CMOS, 10 to 20 milliwatts, 10 dBm to 13 dBm. See how quickly I did that in my head? SiGe, 50 milliwatts to 100 milliwatts. Gas, 2 to 3 watts. And GaN, 10 to 15 watts. And if you go out there and look for real commercial products, you'll find power levels bobbing around this sort of level. So what about the SMT packaging technologies? I've put a typical frequency here. Again, these aren't cast in stone. But for overmolded plastic, typically up to about 30 GHz, you can push it higher depending on the functionality. But for PAs, up to about 30 GHz. And we normally use a custom lead frame, and we optimize that lead frame for best RF performance. Air cavity plastic, we've got an example of this working nicely to about 42 GHz. Again, there's a custom lead frame inside there. Laminate you can push a bit higher. inside of a laminate package, and I'll be showing some photographs. I'll be showing lots of nice clear photographs of MMICs and bonding arrangements. In the laminate package, you can sit the die in a pocket so that the surface you're bonding to is much closer to the surface of the die. That shrinks the bond wires a little bit and allows you to push the upper operating frequency a little higher. Wafer level chip scale packaging. Somebody asked about flip chip. And it is a nice approach. It's not the answer to everything. And it is difficult with PAs because it requires thermal management. Now, the PA die in cellular handsets at 2-3 gigahertz, they're flip chipped. But what they do there is they have large areas on the die that they connect to a metal base of the package. They suck the heat out that way. That's more difficult at millimeter wave frequencies. But flip chip is a technology that people are pursuing. It will see more and more use. And really what happens is in the final stages of the wafer processing, the package processing starts then. Multi-chip modules, there's still a place for these. If you open up most commercially available E-band radios today, you'll see there'll be multi-chips with either wire bonded or tape bonded. Integral antennas, there's some really nice work being done on packaged ICs with integral antennas operating to 100 gigahertz. Again, they have their place. Normally these have multiple antennas and a modest level of power going to each antenna. Of course, when you've made this, you can't then do any filtering. You know, everything's done and dusted. You're using what you've got. That's your entire piece of kit. So you need to be very sure. The more application specific you become, the more highly integrated, the lower you have the opportunity of reducing the cost in very high volumes, but it is then very application specific. So let's start with the first example I'd like to talk about, and that's a 28 gigahertz PA. Now this was realized on a P15 process, which is an enhancement mode process. So that means positive only voltages. And the complete 50-ohm match die with a power detector is there. It's all housed in a 4mm by 4mm QFM package. It's a standard overmolded process, but we have designed a custom lead frame to optimize that RF performance and make sure there are no package body resonances. As your package size gets bigger and bigger, the size of the body becomes electrically significant, and the unwary user can find resonances in band due to this physical size. So, brief performance summary. Frequency range 26 to 30 gigahertz. That's where it worked over. We were actually asked to design this for the 28 gigahertz 5G band, but we designed a bit of guard band and we achieved a bit of guard band. About 20 dB of gain. The P1 dB, some variation across the band, but around about 25, 26 dBm. The PAE at P1 dB is 25 to 30%. Now, this PA was not intended to operate at P1 dB. I've simply put that in there for a metric because people are used to seeing PAEs and P1 dBs quoted at P1 dB. We were asked to design it for operation at minus 35 dBc IMD3, i.e. backed off from 1 dB compression to preserve modulation fidelity. And we achieved 7 to 9% PAE at that frequency. Now that sounds quite low, but I can promise you when you're backed off this far from compression, it's hard to achieve that level of PAE. And what we'll see in the real world, of course, is some form of linearization. I don't believe envelope tracking is really practical for the sort of bandwidths we're looking at for 5G. But I think some form of pre-distortion will be used. I'm going to show you some measurements now and how they compare to the simulations. All of these measurements were made for the package part on the PCB. So it's much easier to probe something with ground signal ground coplanar probes and show good performance there. When you get it in a package, get it soldered on a PCB, that's how it needs to work. So that's what you need to look how you can perform in that environment. So here's our PA here. It's a 3-stage PA. You can see there are 4 output transistors. Now all mmWave PAs of any sensible power level use multiple transistors in the output. And we don't just use one big transistor here, because as the transistor size gets physically larger, it also becomes electrically larger, and the parasitics mean that the gain drops. So you have a balancing act between having a transistor which has a sensible RF output power capability, but still retains a practical level of gain. And so this transistor sizing and biasing is critical. And we put 4 combine nicely, 2 combine nicely, 8 combine nicely. Using above 8 starts to get a bit impractical. Don't try and use 3, it's awful. And we drive this with 2 transistors and then 2 smaller transistors at the input. And the first thing we do in this design is the selection of the transistor size and bias. Getting this right is critical. You can see at the output here, actually I don't know if you can see, but there's a tiny little coupler, and it's a foreshortened coupler. So we make it shorter to save on die area. You sacrifice a little bit of directivity, but it still has a reasonable directivity, enough to give you a good indication of the transmitted power level. So we have these made, we have them fabricated, then we do some measurement on wafer, then we send them off to be packaged. We've designed a custom lead frame in this little 4mm by 4mm. You see it's small, that size, compared to the size of these connectors. And we designed this evaluation PCB. We also designed this TRL calibration PCB. So the center of this line here takes us to the reference planes of this package. So we perform a TRL calibration using that, do all our measurements on that. The measurements are referenced to the ports of this package, soldered down onto a representative PCB, which is Rogers 4003 8th thou thickness. If you're designing one of these PCBs, make sure you use plenty of wires in the ground paddle, or the amplifier will hoot like an owl. This is the measured to simulated performance. The red here is the S21 measured, and the orange is the modeled. And you see we've actually moved up slightly in frequency, but for these frequency ranges, that's a very good agreement. This includes all the packaging effects, the overmolded compound on top of it, all EM simulated, and the impacts of the PCB. We simulated this using ADS from Keysight and the EM simulator which is Momentum. Now, these are measured S parameters. This left-hand side here shows 3 samples of the packaged part we measure. See the input's very nicely matched. That's a 15 dB point there. The output is around about the 10 dB level because, to be honest, we matched it for PAE and linearity rather than S22, but it's not too bad. And the full suite of measured to modeled are showing over here. This is the measured to modeled P1 dB and PAE at the P1 dB point. And you can see the P1 dB, it's very close to measured at the top of the band, a little bit lower at other frequencies, and the same with the PAE. We also did extensive IP3 measurements at various tone separations and various power levels. Our client who paid for this development was most interested in a wide tone separation because 5G will be wide bandwidth. So these measurements are all made at 100 megahertz, and you can see they were done at varying levels, and the IP3 we achieve is similar at all of them. You see that is 1 dB, so it's a very broad, a very small scale. And we're around about the 32.5 dBm level of output IP3. This one is a comparison of the measured to modeled PAE versus Pout, and you see that tracks very nicely. Little bit of deviation in saturation, but at the point we were optimizing the design for, 7 dB backed off, very good agreement. And this shows the performance of the power detector. I've got a schematic of the style of power detector we use here on one of the other examples, but this just shows the output power here versus the detected voltage, which is the difference between a reference and a detected signal. As I say, I'll explain a little bit more about that later, but you can see we're pretty linear here for log voltage against the output power in dBm across all these frequencies, and this works well over temperature as well, being temperature compensated, and you'll see an example of that on one of the other PAs I'm going to show. The next one is a 39 GHz PA. Now this was a higher power PA. We were asked to design something with a 40 dBm IP3. It's still a gas p-hemp process, 0.15 micron, depletion mode this time, and it covers both the 37 and the 39 GHz 5G bands. And the measurement conditions, it's packaged part assembled into a PCB again. Again, the measurements are referenced to the package in the same approach I've just outlined. Lab ambient temperature, 6-volt supply. The last 28 GHz PA I mentioned was a 4-volt supply. And this takes a higher quiescent current. It's biased at 131 milliamps per millimeter. And this quiescent bias point is a trade-off between the small signal gain you achieve and thermal management. It's a microstrip style PCB. The measurements are CW. And this shows the PCB. There's no connectors on this photograph, but I'm sure you can work out where the connectors go. And this is a layout plot of the die. I don't have a photograph of the die for this one because it went straight from the foundry to the packaging facility. But here you can see we've now got 8 transistors. So this you can view as one PA and this almost as another PA combined here. You can see these combining manifolds. 4 shortened coupler at the output again. This is a 4-stage design because we're up now at 40 gigahertz and the available gain per stage is reduced. You can see this is the QFN package. It looks rather like an overmolded. It's ever so slightly thicker and there's an air cavity on there. And you can't tell unless somebody pushes their soldering iron through the air cavity. Then you can tell. This is the measured small signal performance of a number of samples. So reasonable gain across a broad bandwidth, around about the 20 dB level. And this is the P out and the gain and the ID versus the input power. So you can see the output power there, it's approaching 2 watts at saturation. And this is the IP3. Nice, it's reasonably flat all the way from 37 to 42 gigahertz, around about the 40 dBm IP3 level. And this is about the limit of what you achieve in commercially available gas PAs at this frequency. So this next example is a 26 gigahertz PA for the 26 gig Pioneer band. So we were aiming to cover 24.25 to 27.5, and we did with a little bit of guard band. And you can see here, this is a little bit clearer actually, there's the on-chip power detector. This uses 2 transistors, and we're achieving about 26 dBm P1dB. About 30% PAE. This is an on-wafer measurement for this one. This is a 22 dB of gain. You can see this input line here. This isn't a clever piece of design work. It's because this IC, we realized on another mask set with some other things, we had some space, so we put this on there. We had to stretch this input in order to fit in with the arraying. The dimensions of this current die are 3.5 by 1.2 millimeters there. And we can reduce this to about 3 millimeters in the X if we array it on a custom mask set of its own. So this is, I just thought I'd show how this detector works. So you have a reference diode here, and this produces a certain reference voltage here. And then you have a detector diode with no power going through it. The detector voltage is the same as the reference voltage, And so you get the difference between them is 0. As you start putting power through it, this becomes more negative, and so then you get a reference voltage difference. This is the measured S parameters on wafer. 6 volts, 210 milliamps IDS. And this shows how the RF on wafer measured performance match with the predicted. I think you see that's very good agreement of S21. That's the dash traces, the simulated. So we cover 24 to 28, so comfortably encompassing that 26 gigahertz Pioneer band, also the 24 gigahertz US band. We actually designed some guard band, but we didn't need it. We worked all the way up to the top edge. And we've got an S11 of better than 13 dB, and S22 better than 10 dB. This is the RF on wafer measured of 5 samples compared to the simulated in red. All of the individual die look very similar, and the simulated results look very similar, so that's good. Now this is the power compression performance measured on wafer. The P1 dB is there's only 3 points measured here, top, middle, and bottom of the band. It's about 26 dBm P1 dB, about 30% PAE, and then PAE at 6 dB back off is round about the 10% level. And this is a package that we put it in, and it's a custom designed dual channel package. And this was manufactured for us and assembled for us by Filtronic. We use a lot for our mmWave assembly, and they always do a very good job. This package development work was supported by the Compound Semiconductor Applications Catapult, and they have some of these sample evaluation PCBs, which they're evaluating with their impressive 5G test setup. So it's a laminate base here, and we designed these RF transitions here, which just look like a blob drawn by a small child. But you do actually have to get the shape of it all just right in order for it to work. You can see here the cavity where we drop the die. We drop one here, we drop one here. I think I've got an assembly photograph coming up. This is the part when it comes out. It just looks like a QFN package because it is a QFN package. And this is just a little schematic. RF in 1, RF out 1, RF in 2, RF out 2. And this is an assembly diagram. And there's a die here and a die here. You can see we use 3 bonds here. We've got the lengths nice and short, keep the inductance down. Even though you keep the inductance down, you have to absorb it into a cunningly designed low-pass filter using the bond pad here and the shape of your landing pad here. Then you need to design this transition to go down in your PCB again to work effectively. And we designed an evaluation board. It's got 2 inputs here, 2 outputs here. You can see the CSA Catapult logo here. And this is just to show that there are 2 parallel die in here. And we have a TRL calibration tile, similar to the last one, that we use to calibrate and measure the performance reference to the package. And this is what one looks like. We've added some DC cables so we can bias up the amplifiers. And TRL stands for through reflection line. It's a calibration technique to calibrate a vector network analyzer. This is the measured performance of a package component, and this is one typical one, and it shows both channels on the same plot. Fortunately, they match quite well, and there's not much difference between the channels. And this compares the package performance to the RF on wafer, and you'll see it's very similar, and that really shows the quality of the package design and the assembly. And it really works nicely. And there doesn't look much to the package design, but honestly, it's really easy to get it wrong. Here's the measured performance over temperature. And blue is the cold temperature, and you get a bit more gain. red is the hot temperature, and you get a little bit less gain. There's not much variation in the return losses. Here's some performance, how the power compression varies with temperature. And there's less variation in power compression than gain, but you still get a bit more power at cold temperature and a little bit less power at the hot temperature. And we're around about the 26 dBm level at P1 dB. And this is the PAE, again, at 3 temperatures. And same story again, very slightly better at the low temperature, very slightly worse at the hot temperature. This is probably no surprise. And this is the power detector. And we're seeing here the power detector performance for 3 traces at 3 different temperatures. And I think it's quite evident here that the temperature compensation seems to be working well. This is the IP3, which is about 36 dBm, which is quite nice because the P1 dB was 26 dBm. So we've got a nice delta there with this amplifier. There's not too much difference there. It dips slightly at the hot temperature. So this is a dual band PA. I'm not going to go into much detail about this. This differs from all the other PAs I've shown you in that this hasn't been manufactured. This is really just a concept. We think there will be a need for dual band components as 5G matures. The first 3G technology used single band terminal equipment initially, but everything's now multi-band. So this covers 2 bands, the 26 gigahertz band and a 31 gigahertz band. I'll just skip over that. This is a layout plot, and it's electronically switchable. You've got a 4 transistor output, RF output here, and there are various transistors here which switch in and out matching components. So you can electronically switch between the 2 bands. The difficulty with this design approach is accounting for the parasitics because they're not ideal switches. We'd be laughing if it was ideal switches, but they're not. However, you can progress the design and account for these parasitics. And this is the shows the dual band performance. And the blue band is the 32 gigahertz band. The red is the 26 gigahertz band. You can see it switches nicely. And similarly with the large signal performance, it switches nicely. Now, there's more details on our website, and we've also got a YouTube channel where there's a video describing this design for anybody who's desperately interested to find out more. So, to conclude, there's a lot of work underway on the development of millimeter wave components for the candidate 5G bands at millimeter wave frequencies. The operating bands, strictly speaking, are still to be confirmed, but the picture's becoming clearer. All of the first kit will be Ka band. I honestly don't think there's going to be any 60 gigahertz 5G anytime soon. We've presented a number of design examples covering the 28, 39 and 26 gigahertz band, and also a concept design for a dual band PA. There's tons more technical stuff on our website for anybody who's interested. So, thanks.
Thank you very much, Jim. Do you have any questions?
Shall I ask you the easy question or the hard one?
Oh, the hard one.
Okay. How much pre-testing did you do of the 2 chips before you put them in the channel? I mean, was it literally the first 2 off the wafer, or did you...
No, actually, it's even more radical than that. So we tested 5 on a wafer. We sent the wafer off, got it cut up. We got 200 samples. We sent 100 of them to Filtronic, and they randomly picked die from those 100 samples. And we've assembled about half a dozen dual channel units, and all of them work. There's not one failed, even though we didn't test them on wafer. Now, that doesn't mean we've got 100% yield. I think that limits where we can draw the conclusions on inductive reasoning, but the yield we can say is very high.
With the PAs that you've highlighted for 5G, do you expect the PAEs to be at that level, 30% at best, and obviously I'm not talking about the back pocket things, but is 30% the best we can expect?
Yes, in the short answer, you might get 30, 32, 33. You just need to, if you look at Qorvo's website, they're the world's leading manufacturer of PAs. They have a team of highly skilled engineers who've been beavering away for years. The best products they have at mmWave are about the 30% level at P1 dB.
Okay. Yes.
Liam, very interesting, nice results. Did you do a lot of 3D EM simulation of the package and die together?
No, we did we have a 3D model for the bond wires, but everything else was 2.5D EM.